Now we're going to do a more complicated stoichiometry problem. This one is solution stoichiometry with limiting reagent and percent yield. In solution stoichiometry, to get to moles, you'll need to go from milliliters to liters to moles. The liter to mole conversion is accomplished by multiplying by the molarity, right? But there's a shortcut. Molarity equals moles per liter. That's moles per 1,000 milliliters. So, in this problem, we're given that we have 0.0200 molar H3PO4. We can write that as the following equivalence statement. 1,000 milliliters equals 0.0200 moles. When you have a limiting reagent problem, your first task is to determine the limiting reagent. That can be accomplished by simply comparing what you're given, right, the given quantity, with the needed amount. And the needed amount you get from doing stoichiometry. Finally, percent yield. Just remember the percent yield equation. Percent y equals actual yield over theoretical yield times 100. So here is our question. You mix 1,250 milliliters of 0.0200 molar phosphoric acid with 1,510 milliliters of 0.0111 molar calcium hydroxide, and you obtain 1.67 grams of calcium phosphate. What is the percent yield of the reaction? The first thing you want to do is the balanced equation. So we have H3PO4 aqueous plus CaOH2 aqueous yields Ca3PO42. That's a solid, you'll see from your solubility rules, plus H2O, since it's an acid-base reaction, and of course the H2O is a liquid. Now, to balance it, we got 3 calciums on the right. We need 3 calciums on the left, so we put a 3 on calcium hydroxide. That means we have 6 hydroxide ions now. We have 2 phosphates on the right-hand side of the equation, which means we need 2 phosphoric acids. That means we have 6 hydrogen ions. 6 hydrogen ions plus 6 hydroxide ions gives us 6 water molecules. Now our equation is balanced. The next step is to determine the limiting reagent. Okay, so you can start off with the given quantity of reagent A, go from milliliters of A to moles of A, to moles of reagent B, using a mole ratio, 2 milliliters of B needed, and then you compare this with the given quantity. So we'll start with 1,250 milliliters of phosphoric acid. We'll convert it to moles by using the molarity. 1,000 milliliters, that is 1 liter, equals 0.0200 moles of H3PO4. Milliliters of H3PO4 cancels. Now we use a mole ratio to get to moles of CaOH2. We need 3 moles of CaOH2 for every 2 moles of H3PO4. And these numbers are the coefficients in the balanced equation, as we've seen. Moles of H3PO4 cancels. Now we need to go to milliliters of calcium hydroxide needed. How do we do that? Well, our concentration of CaOH2 is 0.0111 molar, which means 0.0111 moles of CaOH2 is equal to 1,000 milliliters, or 1 liter. So now we're going to set up this equivalence statement as a conversion factor. We'll put the number of moles on the bottom, 0.0111 moles CaOH2, and on top, 1,000 milliliters. Now we can punch this into our calculator. $12.50 times 0.02 times 3 times 1,000 divided by, open parentheses, 1,000 times 2 times 0.0111, enter. And we get that we need 3,378 milliliters of CaOH2. Now, how many milliliters of CaOH2 do we actually have? We have 1,510. So, clearly, the amount we need is greater than the amount we have. Therefore, CaOH2 is our limiting reagent. So, CaOH2 is our limiting reagent. That means we're going to use CaOH2 to figure out our theoretical yield. 1.67 grams of calcium phosphate is our actual yield. And we're going to need the molar mass of calcium phosphate since we're trying to find grams of it. Summing up the average atomic masses of 3 calciums, 2 phosphoruses, and 8 oxygens gives us 310.2 grams per mole. So, let's find our theoretical yield now. We have 1,510 milliliters of CaOH2. We'll convert it to moles using the molarity. 0.0111 moles of CaOH2. On the bottom, 1,000 milliliters. Milliliters cancel. Now we have moles of CaOH2, and we need a conversion factor that is a mole ratio. And let's see here. The coefficient on calcium hydroxide was 3, so we put 3 moles of CaOH2 in our denominator. That means moles of CaOH2 cancels. We're going to calcium phosphate, and the coefficient on calcium phosphate is 1. So we put 1 mole of Ca3PO4 in our numerator. Finally, we need to get the grams of calcium phosphate produced. And so we use the molar mass, put 1 mole on the bottom. Moles of calcium phosphate cancels. Up top goes the molar mass, 310.2 grams. Now we're ready to do our calculation. So 1510 times 0.0111 times 310.2 divide by open parentheses 1,000 times 3, close the parentheses, press enter, and we get 1.73 grams of Ca3PO42. That is our theoretical yield. What is our percent yield? Well, percent yield just equals the actual yield over the theoretical yield times 100. The actual yield we were given was 1.67 grams. The theoretical yield we just calculated, 1.73 grams. Multiply the result by 100 and we get 96.5%. Now you try this question. What is the percent yield if mixing 50 milliliters of 1 molar calcium nitrate with 50 milliliters of 1 molar sodium phosphate produces 5.01 grams of precipitate? And the balanced equation is given to you. Remember, the first thing is to identify the limiting reagent. The second thing will be to use stoichiometry to find the theoretical yield. And the third thing will be to find the percent yield. Pause your video now and do the calculation, and then restart the video to check your answer. So to determine the limiting reagent, we're going to compare what we have with what we need. We'll start off with 50.0 milliliters of CaNO32. We're going to convert that to milliliters of Na3PO4. First thing is to convert it to moles using the molarity. We'll put 1,000 milliliters in the denominator and 1.00 moles in the numerator because our concentration is 1.00 moles per liter. That's 1.00 moles per 1,000 milliliters. Milliliters cancels. Now we need to go from moles of calcium nitrate to moles of sodium phosphate. We put 3 moles of calcium nitrate in the denominator because the coefficient on calcium nitrate is 3. 2 moles of sodium phosphate in the numerator because the coefficient on sodium phosphate is 2. Moles of calcium nitrate cancels. Final thing, we use the molarity of sodium phosphate to get milliliters of sodium phosphate. Now we put the 1,000 milliliters in the numerator and the molarity, 1.00 moles, on the bottom. Moles of sodium phosphate cancels. We see that we need 33.3 milliliters of sodium phosphate. Okay, so 33.3, what we need is, less than the 50.0 that we have. That means that sodium phosphate is the excess reagent and calcium nitrate is the limiting reagent. So now we know that calcium nitrate is our limiting reagent. It's time to find our theoretical yield. We're going to go from milliliters to moles to grams. And we want to start with milliliters of our limiting reagent. So we have 50.0 milliliters CaNO32. Convert it to moles. 1 mole of CaNO32 over 1,000 milliliters. Use the mole ratio to go to moles of calcium phosphate. Oh, let's cancel as we go. Milliliters cancel. Now we have 3 moles of calcium nitrate in the denominator. Moles of calcium nitrate cancels. In the numerator, we have 1 mole of calcium phosphate. Finally, we want to go to grams, and it's 310.2 grams in 1 mole. Moles of calcium phosphate cancels. Plugging into our calculator, 50 times 310.2 divided by parentheses 1,000 times 3, close parentheses, press enter, and we get 5.17 grams of Ca3PO42. That is our theoretical yield. Now, percent yield equals actual yield over theoretical yield times 100. The actual yield is 5.01 grams, is given in the equation. We just found the theoretical yield of 5.17 grams multiplied by 100. And we get 96.9%. Thanks for watching.